Hello, budding scientists. Let me ask you, when someone says, prove it, what's your go-to? You pull out evidence, right? Well, in physics too, we don't just believe laws because they sound fancy. We test them. Today, we are going to experimentally verify the laws of reflection. Here's the setup: a drawing board with a white sheet of paper, a line mm1 for the mirror base, and a point O. From O, we draw an incident ray OW. Then, we construct a normal on at O and place a plane mirror vertically along mm1. Simple, right? Just a mirror, a few lines, and some pins. Yet with this, we can prove the very foundation of optics. Now let's trace the incident ray. We fix two pins, P and Q, vertically about 5 cm apart along the line OW. These two pins act as markers showing us exactly where the incident ray travels towards the mirror. Then, we peek from the other side of the normal and spot their images in the mirror, P' and Q'. These virtual images help us see where the reflected ray should emerge. It's a little like lining up dominoes. You set the first two, and the rest of the path becomes obvious. Here, pins P and Q define the incoming ray with surgical precision. Now the fun part, tracing the reflected ray. We place pin R so that, when viewed in the mirror, R appears perfectly aligned with the images P' and Q'. Then we add another pin S in line with them, just to be sure. What happens now? Pins R and S show us the direction of the reflected ray, orb. Connect O to R and S, and you've got your reflected beam. So, using nothing but pins and patience, we've drawn both the incident and reflected rays without guessing a single angle. That's physics craftsmanship. Alright, time to test the first law. Measure the angle between OW and ON, that's the angle of incidence, denoted I. Then measure the angle between orb and ON, that's the angle of reflection, denoted R. When you record the data, you find something magical, I equals R. For example, if OW makes 40 degrees with ON, then orb also makes 40 degrees on the other side. So mathematically, I equals R. And there you have it, the first law of reflection, proven with nothing more than pins, a board, and some careful eyes. Now we don't stop at one measurement, no scientist trusts a single reading. So we repeat this experiment for incidence angles of 30, 40, 50, and 60 degrees. Here's the observation table. When I equals 30 degrees, R equals 30 degrees. When I equals 40 degrees, R equals 40 degrees. When I equals 50 degrees, R equals 50 degrees. When I equals 60 degrees, R equals 60 degrees. Every single time, incidence angle equals reflection angle. The law holds firm like a loyal friend. No exceptions. Now let's check the second law. Remember, it says the incident ray, the reflected ray, and the normal must all lie in the same plane. In our setup, everything is pinned on a flat drawing board. All four pins, P, Q, R, and S, align on the same sheet of paper. That proves the rays and the normal don't sneak out into 3D. They stay coplanar. So both laws are verified, I equals R, and all three lines, incident ray, reflected ray, and normal, lie in the same plane. Two laws, two victories. Let's do a worked example. Suppose the angle of incidence is 40 degrees. Step 1. By the law of reflection, I equals R. So the angle of reflection is also 40 degrees. Step 2. What's the angle between the incident and reflected rays? Easy. That's I plus R. So 40 plus 40 equals 80 degrees. Final result, reflected ray makes 40 degrees with the normal, and total separation between incident and reflected rays is 80 degrees. This quick calculation is exactly what we verified with our experiment. Simple, neat, and exam-friendly. So let's tie everything together. Our pin and mirror experiment has given solid proof of the two laws of reflection. First law, the angle of incidence equals the angle of reflection. Second law, the incident ray, the reflected ray, and the normal lie in the same plane. And the data, 30, 40, 50, 60 degrees, all confirm these laws. It's amazing that such a simple classroom experiment validates the very principles that guide periscopes, kaleidoscopes, and even space telescopes. So, the next time you place pins in a physics lab, remember, you're retracing the path of scientists who confirmed how light obeys rules, always, without fail. That's the beauty of physics, big truths revealed by small experiments. See you in the next concept.